All right, I think we're ready to go. My name is Scott Stoltz. I'm one of the founders of OSC, and it's my pleasure to introduce Trey Grainger. Trey is the Chief Algorithms Officer at Lucidworks, where he drives vision and practical application of intelligent data science algorithms to power relevant search experiences for hundreds of the world's biggest and brightest companies. He is also the co-author of Solr in Action. Oh, it's a big one. Plus more than a dozen additional books, journal articles, research publications covering industry-leading approaches to semantic search, recommendation systems, intelligent information retrieval systems. Trey received his Master's of Management of Technology at Georgia Tech, studied computer science, business, philosophy at Furman University, and studied information retrieval and web search at Stanford University. Trey?
All right. Wow, I didn't know you were going to go through all that. Welcome, everybody. What's that?
Just killed your slide, too.
My slide, too. There we go. All right, we'll skip over this slide. I'm Trey. I'm going to talk to you about search. So the topic for today is natural language search with knowledge graphs. And this is the agenda we're going to go over. Quickly talk about Lucidworks. I think everybody in here probably knows who we are, but briefly. Talk about what a knowledge graph is and also related terminology, ontologies, taxonomies, et cetera, what it all means. What is natural language search? Spend a little bit of time on philosophy of language. Anyway, enough so you sort of understand where I'm coming from with what you're going to see. Then I'm going to talk about Solr semantic knowledge graph, the knowledge graph goals, the goals we try to achieve with knowledge graphs for natural language search, semantic query parsing, including two of the open source components in Solr, the Solr text tagger and the statistical phrase identifier, and then talk about sort of having a full knowledge graph with everything integrated together in Solr, and then talk briefly about automated generation of knowledge graphs, and then do some demos at the end. I'm excited to show this stuff off. How many of you guys have come to a talk of mine before on the semantic knowledge graph, knowledge graphs, any of this kind of stuff? Okay, cool. So I'm going to review some of that material, but I'm going to try to go through it kind of quickly. You guys can always refer back to old presentations as needed. And who saw my talk at Activate last year also? Not as many. Okay, cool. All right. I know what topics to spend time on then. So if you've come to any of my presentations before, you've probably seen this slide. This is my sort of notion of relevance engineering sophistication. Most people start at the bottom left with basic keyword search. They sort of, after they realize it's not sufficient, start thinking about taxonomies, entity extraction, ontologies, those kinds of things. Eventually move on to query intent and actually trying to interpret and parse the query, query intent classification, concept expansion, clustering and classification, other machine learning approaches to just really understand what the user's typing in. People always do some relevancy tuning at the end, but starting to really get into things like learning to rank, neural networks, automated A/B testing or back testing, those kinds of things, and then eventually. I've sort of gone through this journey over the course of my career, as have many of you. Eventually, you get to the point where you realize that the things you're doing manually, many of them can be automated, and you can start looking at ways that all of these things can be learned automatically. So you get this sort of feedback loop where you've got a self-learning system. And I tend to, in a lot of my work and talks, focus on that higher end of the spectrum and trying to automate the things at the bottom end. But obviously, along that journey, there's a lot of things you have to do manually, and some things that we may never be able to automate. But I always try to do as much as possible. So in this talk specifically, I'm going to be talking about this sort of middle tier, taxonomies, entity extraction, and query intent, and I'm going to be staying away from any topics at the upper end, just to give you context for what you're going to see today. So about Lucidworks, we're commonly known as the commercial company that provides support for Solr and development for Solr. We employ about 40% of the active committers on Solr and generally contribute about 70% of the open source contributions to the code base. We're based in San Francisco, have about 230 240 employees, about 400 customers across the globe, and we sponsor Activate, the Search and AI conference. I would say that basically Haystack and Activate are, in my mind, the two best conferences to go to understand relevancy in search. So, definitely, we'd love to see you guys there this year. We also have a commercial product called Fusion. Many of you use it, I think, and it basically embodies a lot of the relevance techniques that you've heard about at the conference this week. It's sort of an out-of-the-box platform. We've consistently been sort of moving up in the analysts, so we're very solidly in the upper right leaders quadrant at this point for our Fusion product. And I mentioned Activate, by the way. Anyone who's spoken here or has done something really interesting, our call for speakers is actually open for this year, so I think it closes May 8th. So if any of you are interested in presenting at Activate, I definitely recommend submitting a talk. Okay, so that's enough about Lucidworks. Let's talk about knowledge graphs. So what is a knowledge graph versus an ontology versus a taxonomy versus synonyms list, et cetera. So if you search for knowledge graph in Google and go to Wikipedia, Google, when you search for knowledge graph in Google, it automatically takes you to the Wikipedia about Google's knowledge graph. I think actually Wikipedia tends to go to that one as well. But if you go to, and then it refers you back for disambiguation to ontology. In the ontology Wikipedia page, it says that although there is no clear definition for the term knowledge graph, it is sometimes used as a synonym for ontology. One common interpretation is that a knowledge graph represents a collection of interlinked descriptions of entities, real-world objects, events, situations, or abstract concepts. Unlike ontologies, knowledge graphs, such as Google's knowledge graph, can often contain large volumes of factual information with less formal semantics. I'm going to give simplistic definitions for all this stuff. In my mind, when I'm talking about, at least in this presentation, when I say an ontology, it's something that defines relationships between types of things. So for example, an animal eats food, a human is an animal. When I say knowledge graph, it's an instantiation of an ontology. So it contains things that are related. So for example, John is human, John eats food. It's sort of a specific fact being described. A taxonomy is something that classifies things into categories. So for example, John is human, human is mammal, mammal is animal. And a synonyms list is something that provides substitute words that can be used to represent the same or very similar things. So human is a Homo sapien, or maps to Homo sapien or mankind. Food maps to sustenance or meal. There's overlap between these. Some of them have heavy overlap. Actually, Doug posted something back in December called A Synonym by Any Other Name, a blog post, and he kind of broke these out. You'll see in his, that top level is knowledge graph, and he doesn't even have ontology on there. He's basically assumed that they're more or less the same thing because there can be heavy overlap there. Then he's got taxonomies as a subset of knowledge graphs, synonyms as a subset of taxonomies, and then alternate labels are those as a subset of synonyms in there as well. So it's got a really good blog post if you just want to read up on this. But because I am recommending his blog post, I also need to caveat something, which this talk is actually about. So in his blog post, he talks about the Solr, knowledge graph, and elastic graph plugins. And he says, just to let you know, these aren't the same as a formal knowledge graph that we describe here. They lack verbs. Instead, they are really interesting in their own right, learning what terms are connected based on co-occurrences. You must decide what those co-occurrences mean in your data for your domain and use case. So I'm going to actually say for Solr, I strongly disagree with that. But I'll get back to that later with some demos at the end. So what is natural language search? Very easy. It's talking to the search engine in natural language. Who is Barack Obama? What is Avengers Endgame, for example? It's not having to use Boolean logic and not having to use traditional search keywords. You can just ask the search engine something. So for example, in this case, from one of our question answering systems, can my wife drive on my insurance? And then you get documents or answers back answering that question. What kind of knowledge can help us with the kinds of problems we encounter in search use cases? So we'll get into the semantic knowledge graph in a few minutes, but when we published, so I worked on the semantic knowledge graph, sort of came up with the initial idea. We published a research paper on it a few years back, and this is what we laid out in the research paper in terms of why we developed it, just to give you some insights. So because current knowledge bases and ontology learning systems typically require explicitly modeling nodes and edges into a graph ahead of time, this unfortunately presents several limitations to the use of such a knowledge graph. For example, entities not modeled explicitly as nodes have no known relationships to any other entities. Second, edges exist between nodes, but not between arbitrary combinations of nodes. And therefore, such a graph is not ideal for representing nuanced meaning of an entity when appearing within different contexts, as is common with natural language. Third, substantial meaning is encoded in the linguistic representation of the domain that is lost when the underlying textual representations are not preserved. Won't get into all the details there. And last, it can be an arduous process to create robust ontologies or taxonomies or knowledge graphs, map a domain into a graph representing those ontologies, and ensure the generated graph is compact, accurate, comprehensive, and kept up to date. And so those are some of the problems we were trying to solve when we built the semantic knowledge graph. And you'll see how that works in a bit. So we're going to talk a little bit about philosophy of language. Some of you may have seen this before, but bear with me if so. Usually when we talk about unstructured data, we're referring to text, free text. And it's what we often deal most with in search. We obviously have support for other attributes as well. But there's this notion that the free text is hard to deal with, hard to understand, hard to score, hard to use. And so my sort of philosophy of language, my three assertions I'm going to make today are, bear with me. These, you have to think about these a little bit. The first, unstructured data is actually hyperstructured data. It's a graph that contains much more structure than typical structured data. Two, that graph is very rich, but is a compression of meaning into a lossy format, into text. So you're taking lots of things and relationships being represented, and you're compressing them into text, and you lose context when you compress them to text in terms of what the original intent was. Much of data science is actually the decompression from this lossy format into a reconstituted form. So I've got a bunch of data points, I've got a bunch of words, and I'm trying to map them back into some concept. I'm trying to map them back into some meaning. That's largely what data science does. And there's some problems when you sort of go from the actual data and you generalize it to a model. As they say, all models are wrong, but some are useful. Whenever you are creating a classifier, for example, it's not completely right, and you might put something into a bucket where it could actually belong in multiple buckets. And so there's a lot of nuance that you just miss when you don't have that original context of the text. And then most important, every instance of a word or phrase you ever encounter has a unique meaning. And so let's go through these really quickly. So first one on unstructured data being hyperstructured. So this is typical structured data, right? I've got discrete values over here on the left in my ID field. I've got continuous values in my date field. And then we've got this notion of a foreign key. Okay, fine. I understand this is a particular identifier that can map between multiple tables or instances. And then this is unstructured data. Trey Grainger works at Lucidworks. He's speaking at Haystack 2019. Haystack Conf is being held in Charlottesville, April 22nd through 25th, 2019. Trey got his master's from Georgia Tech. What do you do with that? If you take that as sort of individual pieces of data, combine some other things, take a picture of me, take a video that has my name in it, maybe my voicemails, and start looking at these things kind of like we did in that table example. I see oh, hey, there's this word haystack. It's actually represented in two different pieces of unstructured text, two different documents. That's kind of like a foreign key, right? Then I've got Trey Grainger and Trey. Both of those refer to the same entity, even though it's a different word and variation. Let's call that a fuzzy foreign key. There's some sort of entity resolution going on when I map between those. This is an even fuzzier foreign key. I've got pronouns. I've got my name appearing in text in that video on the right. I've got a picture of me. These all refer to the same underlying entity. They're all keys, foreign keys, fuzzy foreign keys back to that entity. But not so fast. This guy terrifies me. If you search for me on Google and look through all the results, this guy comes back. And I thought this was a mistake. I had no idea what, but actually, apparently his name is Trey Grainger, And I don't know if that's really him or if that's just his profile picture, but every time I search for myself in Google, it terrifies me. Don't search for yourself in Google. If I then continue on, though, and look at all these relationships, then what I actually have from this little bit of unstructured text is this giant graph of relationships. Lots of terms that I can relate between documents, and it's there's so much more meaning and structure here than you would find in traditional structured data. So again, my assertion number one, unstructured data is actually hyperstructured data. It's a graph that contains much more structure than a typical structured data. I think we're good there. Everybody hopefully is sold. Assertion 2, that graph is very rich, but is a compression of meaning into a lossy format, text. Much of data science is essentially decompression from this lossy format into a reconstituted form. So if you think of just the nature of language, at the top, I don't know, can you guys read that? If not, well, I'll explain it to you. At the very top level, we've got character sequences. So like for engineer, E, EN, ENG, ENGI, sort of continuing to the right. You build those character sequences, and they even encode semantic meaning inside of them, and prefixes and suffixes and character sequences. Eventually you get enough characters where you have a term, and then you build multiple terms together, and you get a term sequence or a phrase, and then you take multiple term sequences and you build them together into fields, and you build the fields together into documents, and you're building up these combinations of semantic meaning all throughout the document. And that meaning and context is really important, and you can learn a lot from it and use it in lots of ways. So how do we easily harness the semantic graph of relationships that we just saw with unstructured information, within unstructured information? So search engines, obviously, are really good at querying across character sequences, term sequences, and documents. I can do something like C?O, which will match CTO, CEO, CFO, VP of engineering within two positions of each other, and then obviously complex Boolean logic. I can interrogate this graph, all these relationships, and find answers out of it. It's really easy with the search engine, based upon the way it works, where you basically have a lookup of terms and you do your intersections in your inverted index. But one of the really interesting things, if you think about the inverted index, which I have represented over here on the right, the term doc inverted index, that maps from particular terms to documents. But we also have structures when you're doing faceting in Solr or aggregations in Elasticsearch. You have also this forward index that can either be built at query time in Solr by uninverting the field, or if you ever use doc values on a field, you're building this data structure at index time that actually maps from documents back to terms. So if I can map from terms to documents, and I can map from documents to terms, I can obviously go term doc, doc term, term doc. I can traverse through these relationships in very interesting ways, which is where the semantic knowledge graph comes in. So the semantic knowledge graph is think of it like an API. It's a data science toolkit that allows you to calculate similarity between terms, phrases, and queries. So the way I would think of it very generally is usually when you query the search engine, you're typing in a query or terms, and you're trying to match documents and find the documents that match the most. With the semantic knowledge graph, you're querying with query or terms, and what you're finding back are queries or terms. They're entities in field. So find me the most related terms for this term. Find me the most related companies for this term. Find me the companies that are most related to this category and also this term. Those are the kinds of queries that you're issuing. So I mentioned the inverted index lookup and the forward index lookup. It basically allows you to do things like query for Java in the skill field in my job search document, find all the documents related to that, then traverse to some other skill, maybe in this case it's Scala, and then from that traverse to a job title field and find me the most related terms and titles along the way. And so from a graph point of view, I've got this graph over here that represents each of the terms and phrases and then the edges between them based upon the kinds of fields that they're found within. From a data structure point of view, anyway, you can refer back to this in other presentations I'm given. I don't want to spend too much time on the internals, but one thing that is important to understand is the way that it does the scoring. And so it's very similar to a z-score, but effectively, if I have a query like the word Hadoop, and I have a list of terms that are found: Beehive, teacher, Java, .NET, registered nurse, Java. What it does is it says which of these words are the most semantically related to Hadoop based upon the similar context they're found within. And so Hive gets a really high relatedness score. Java gets a high score but lower than Hive. .NET gets a positive score but not so high. B has no correlation, it's probably not in the index. And teacher and registered nurse have a negative score because in general, documents about Hadoop are less about teachers and less about registered nurses than any random document. And so with this and with this ability to traverse between nodes and edges, we now can do something like generate a node on the fly, a materialized node for software engineer star. So anything that's software and engineer with a wildcard, make that a node in my graph and traverse from that node to any list of other queries or terms. Give me a rank based upon how semantically related they are, and then from those I can continue traversing on as far as I want. And so the example, we originally made the semantic knowledge graph. It's actually committed to Solr now, which I'll talk about in a bit. But originally the semantic knowledge graph was a standalone plugin. So this is an example that's in the GitHub repository for it. And this query basically is, I'm going to query for the phrase data scientist. I want to find the top one job title that is the most related to data scientists semantically, and then find the top 5 skills most related to that job title that's related to the keywords data scientist. And within those 5 terms, also include Java explicitly and score it against the others. That's the semantics of what this is saying. And what I get back from that is the top job title for the keyword phrase data scientist is data scientist with a 0.989 similarity. So yeah, it's working. And then the top skills associated with that job title associated with data scientists are machine learning, predictive modeling, artificial neural networks, Apache Hadoop, and Java. Java's only in there because I explicitly said to include it. You'll notice that it has a much lower score. And I need to update this slide because this was from like 4 or 5 years ago. That should probably say Spark now instead of Hadoop, I would guess. As another example of a query to the semantic knowledge graph, this one's easy. I'm just saying I've got the term Advil, and I would like to find the top 20 terms that are the most semantically similar to Advil. So I get back Advil, Motrin, Aleve, Naproxen, ibuprofen. This is just from a random text field from my content. This is like a health stack. This is the health stack exchange data set for reference. Another thing I can do with the semantic knowledge graph is take a document, extract the phrases out of it, pass those to the semantic knowledge graph, and then in this case, I've got a content-based recommender that's blows more like this out of the water. In this case, I've got a Lucidworks UI developer job description, and I passed it in, and the semantic knowledge graph said, here's the top 5 or 6 keywords that best describe this document. JavaScript, CSS, AngularJS, Semantic HTML, front-end, and web standards. Out of all the terms and phrases in there, those are the most semantically related to this document itself. And here's an example that I've given before. I want to ask the semantic knowledge graph a question. Who's in love with Jean Grey? Most of you probably know the X-Men. If not, sorry. But I basically am sending this in. I say, search on the phrase Jean Grey, traverse to a node that I'm going to make up on the fly that is the phrase in love. And then from that phrase, traverse to the top 5. This is unigrams. I just indexed a bunch of random text. The top 5 individual terms that are the most semantically related to Jean Grey through in love. What do I get back? Jean Grey, OK, good. She should be included. Cyclops, Xavier, and Wolverine. Well, if you know the X-Men at all, you would expect Wolverine and Cyclops to be there. Xavier feels like a little bit of an oddball. Turns out that was actually a thing. And on Stack Exchange, the Stack Exchange sci-fi data set, there's people who talk about how the professor actually had a thing for Jean Grey in some of the comics, and it was creepy. And so I didn't know that, but because that's represented in the textual information in my content, that relationship gets surfaced. If somebody had explicitly modeled this out in a graph, it might have been missed, but the data is driving this, and all of this was done automatically on the fly. I didn't have to model anything. This is just using my inverted index. So assertion 2, that graph is very rich, but is a compression of meaning into a lossy format, text. Much of data science is essentially a decompression from this lossy format into a reconstituted form. And final assertion, and then we'll get onto the fun stuff. Every instance of a word or phrase you ever encounter has a unique meaning. So we obviously are all familiar with things like misspellings, synonyms, ambiguous terms, related terms. These are all, the way I think of it is, these terms on the right are labels that represent some concept. And we're trying to, as best as possible, find that concept for a user. And so actually, just for the sake of time, I'm going to skip through a few of the slides here. I've got a section here on disambiguation, which I've gone over in previous presentations. So I'll skip over it, but I can talk about it at the end if you guys want. But we'll do this one. When I say the word Facebook, what do you guys think of? What does that mean to you?
Social network.
Social network. Software company? Anybody else? Tempering? Election. Tampering, election tampering. Okay, got it. Anybody else? People network. Okay. To some people, Facebook is an employer. To some people, it's a competitor. To some people, it's an addiction. To some people, it's the thing that my parents use to communicate with their friends, but I wouldn't go near it. For an employee of Facebook on Monday, it's a place they're dreading going, possibly. And on Friday, it's a place that they're really happy they're getting a paycheck from. What I'm arguing basically is that word Facebook carries a different meaning depending upon the context within which it's found. And it's not just that Facebook itself, if I say apple, you might say, oh, there's the company and there's the fruit, and you might come up with some categories, back again to that notion of all models are wrong, but some are useful. I'm basically arguing that every term or phrase is effectively a context-dependent cluster of meaning with an ambiguous label. So it's context-dependent. Whatever context I'm in at the time defines what I'm meaning by it. It's a cluster of meaning based upon all my experiences and the context I'm in, and it has an ambiguous label. That word FACEBOOK is a label that I'm applying to some concept, but the concepts to which I'm applying it can constantly change based upon the context. So another example, and then I'll get off the philosophical stuff. What does the word love mean? You've probably seen this example from me before if you've come to these talks, but if I just search for love from the semantic knowledge graph by itself, I get words back like accordance, admiration, adoration, and adore. But if I say, what is love in the context of hug? I get different set back. Caress, cuddle, fondle, pet. They're still about love, but they're a different context of love. It's that word love, but within a different context. What is love within the context of a child? It's angel, babe, baby, cherub, darling. Again, specific labels, depending upon the context you're in, carry a different meaning. So I would argue that typically when we talk about words and phrases and things in the search engine, we're really needing to bring that context with us to be able to understand the nuance, to disambiguate, and really help the users find what they're looking for and match the user's intent. So hopefully those assertions make sense to you. Why is that important, though? As we get into the implementation here, I think it's much more important to intuitively understand the kinds of problems we're trying to solve in natural language search than to jump headfirst into a solution. Because often building the wrong thing can be worse, much worse than not doing anything at all. And once we have an intuitive sense of the problems, then we can confidently use the tools I'm about to describe to build the right solution for your specific domain. And so what's the use case here? Well, obviously, if somebody's asking a question, who is Donald Trump? What is the company Tesla? They're often looking for a specific answer, and if you can determine that, give them that answer. But more often than not, what you have to do is rank. You have to say, well, I'm looking for a bunch of documents about this thing, and I need to rank them. So I'm going to skip over the question answering stuff. Again, that's not what this talk is about. And go straight to how do you rank? How do you understand user intent well enough to rank? And so the goal here, if you think of this query I have at the very top, of machine learning, research and development, Portland, Oregon, software engineering, Hadoop, Java, the out of the box, Lucene and Solr are going to just break that up into machine and learning and research and development and Portland, or software and engineering Hadoop and Java. And we might get okay results on the top page based upon how BM25 or whatever we're using ranks, but we're going to be missing content, and we're going to have extra content. Our precision and recall are going to be all over the place. And fundamentally, we've misunderstood the user. We've not understood their intent. And so a better parsing would be what I call semantic parsing, which is where we at least identify the phrases. So machine learning is a phrase, research and development is a phrase, Portland, Oregon is a phrase, et cetera. And then at least we can match the text appropriately within context. But better than that is understanding semantically what they mean and being able to search conceptually on what they're asking for, not just on the text that they typed in. So this one at the bottom is the more representative of that, where machine learning is like data scientist and data mining and artificial intelligence. Portland, Oregon is understood as a location, so I'm also doing a geo filter within 50 kilometers around, those kind of things. Right? I'm really modeling to the engine what is the meaning for this user who ran the search. And so at Lucidworks, we've got a lot of tools that we work with. Obviously, Apache Solr. We've got the Solr text tagger, semantic knowledge graph, statistical phrase identifier, lots of capabilities in Fusion for semantic query pipelines, AI automatic discovery of synonyms, tokens, phrase head-tail analysis. We've got a lot of components for building this. And in the past year, Lucidworks has added the following capabilities to Solr, directly to open source. So Fusion's proprietary. I'm not going to talk about that stuff today, but these are the things that are in Solr now: the Solr text tagger, semantic knowledge graph, and the statistical phrase identifier. So I'm going to talk about those here. And if you want to know more about the stuff in Fusion, you can look at my Activate talk from last year on building a semantic search system. But for now, let's talk about how we can combine these things together. So effectively, for parsing of a query, the way I approach it, at least, is leveraging two things. One is an FST in Lucene, which we use through the Solr text tagger, which is the tag handler in Solr. I'll show it to you in a second. And the second is a probabilistic query parser. There's something called the statistical phrase identifier that is in Solr. And effectively, if you take a query like software engineering Hadoop Java, the goal is to parse that thing out into the terms of phrases we understand and to be able to represent them. So the statistical phrase identifier, just for reference, this is all I'm going to say about it here. It does something like this. I'm taking a query for Darth, Vader, Obi-Wan Kenobi, Anakin Skywalker, Toad, X-Men, yada yada, a bunch of terms. And statistical phrase identifier uses the statistics in the inverted index to automatically parse terms into phrases based upon the statistical likelihood of it being a phrase versus just terms. So this is basically if I don't have anything modeled, if I don't have explicit terms and phrases and synonyms, this says just punt to the index and just have it try to automatically figure out what the phrases are based upon what all the unigrams in the index and how they combine. So it's a pretty cool tool. It's experimental right now in Solr, so I don't necessarily recommend using it. We're still playing with it, but it is there, and you can download the open source project and kick it off and play with it if you're interested. More interesting for this talk is the tag handler in Solr, the Solr text tagger. Effectively, hold on, let's skip over. Effectively, what it allows you to do is to have an index that has terms in it, to then post content, queries, or documents, and to automatically extract out terms or phrases if they're found in your index. So for example, I can create an index with millions and millions of, if I use the GeoNames database, millions and millions of city names, or millions and millions of company names, or skills, or any kind of attributes or things I would want to use in my domain, put them in the index, and then take some text and pass it to Solr, and Solr will effectively highlight in that text every place where any instance of those millions of things occurs. So it's kind of like reverse highlighting, if you want to think of it that way. It's naive entity extraction. So if I've got a list of entities, I can extract them out of text at very high scale very quickly. And so with those tools, we're going to now come back, and I'm going to do a demo in a second. I want to come back to this. So Doug in his post mentioned that the graph capabilities are really cool, but they're not a knowledge graph in their own right. They're learning what terms are connected based on co-occurrences. You must decide what those occurrences mean in your data. And so based on this presentation thus far and what you guys have seen, I think that's actually a fair conclusion to make. All the examples you've seen to this point were from the standalone plugin, not from what actually got committed to Solr. But when we committed the semantic knowledge graph to Solr, we actually gained full graph capabilities and a lot of power. And so those APIs you saw earlier were for a standalone version. When we integrated the semantic knowledge graph into Solr, we actually integrated it as part of faceting. So you can basically use faceting, and at any point in your JSON nested facets, you can invoke the semantic knowledge graph and traverse from the terms or queries there to other terms or queries, which basically means you can mix and match the semantic knowledge graph with other kinds of query parsers and handlers and things, including the graph query parser, which can traverse between documents. So it's more verbose than what I showed you earlier. That Jean Grey example over here on the left now is a little harder to read and a little harder to write, but there's so much more power that we decided it was worth the trade-off. And so the graph query parser I mentioned allows you to go from terms and traverse to other documents. What if we could, and this is what an example query to Solr looks like. So query's up here on the top, and I'm basically saying search for the phrase haystack and find me all documents that have where the name matches the venue in my haystack document. So search for haystack. If it has a venue field, pull back the documents that have a name. It's like a multi-dimensional join, basically. And so I get back the violet crown, which is where we are. But I can also use this in faceting. So instead of just querying using graph query parser, I can create a facet where the first level of my facet is a query facet. I do a graph traversal there to find all the documents that match, and then within those, I can pull back fields. So in this example, in my faceting, I've now traversed from my original query of haystack, and I've brought back the violet crown, even though and I've got the latitude and longitude for the violet crown location, even though that wasn't in my original document. I've traversed to it. Similarly, for remaining keywords, this example is finding the type of document that keyword maps to, and the related terms for it. So in this case, I'm searching for barbecue near haystack, and I didn't put haystack in here, sorry. This is just I'm searching for barbecue, and in this case, I'm saying pull me back the top related terms to barbecue, so I get BBQ, brisket, ribs, and pull me back the type of document, the classification that this keyword would fit in, and I get restaurant. And so what I can now do is use restaurant as a filter on my query, as a classification or a boost or whatever you want to do with it, and then I can use those terms to do that expansion that we saw earlier. Also, just very briefly, just for the sake of time, if you want to get entities on your documents, there's tons of NLP libraries out there, OpenNLP, SparkNLP, Spacey, all kinds of stuff. If you want to extract entities and put them on your document so that you can use them in your graph. There's also this domain called Open Information Extraction. And I've got an example I can show you guys here where you can basically take some text and automatically extract RDF triples out of it. The technology's hit or miss depending upon how well formatted your text is, but you can automatically learn RDF triples and map them into your content, and then use these graphs to traverse and do interesting things with it. So let's do a demo. So this is basically combining the Solr text tagger and those graph queries I was just showing you a second ago into a live demo, which nothing can go wrong, I'm sure. It will probably help if... OK. So what are we looking for? In my, I'm going to use the example from my abstract for the talk. Barbecue. So what I've got here, if you can read it, I've got 3 rewritings here. The first rewriting is just the things that I've extracted out of my query. The second, extracted or C. The second is me transforming it into some internal representation of the query. And the third is me doing my rewriting phase to send this to Solr. So I typed in barbecue. It doesn't know what barbecue is, but it looked it up in the index and found out that barbecue is like ribs and brisket and pork, and that it's in the category of restaurant. Barbecue near. So in my text tagger, I've got this type of document that's a command that basically says when I see near, that's a location distance for the thing that comes after it. Barbecue near haystack. So what I'm doing here is same thing. Barbecue, don't know what it is, just treat it as a normal keyword. Near is a location indicator saying that the thing that comes after is something that's supposed to have a latitude and longitude. And then because my document for Haystack doesn't have a latitude and longitude, it's saying, let me see if this thing is supposed to have one or has a venue or something where I can find a latitude and longitude. So it then does a graph query in my knowledge graph to go find the place, in this case the Violet Crown, that is where Haystack is located, pulls back that latitude and longitude, and then applies it here as the part of the search. This is all just using Solr, facets, semantic knowledge graph, graph query parser. I've got some misspellings in here, so I can say, Haystack, that works fine. I can say, notice that as I type, if I type H-A-Y, Hay is actually a location, so at the moment it, is interpreting it correctly, but as I continue typing, you'll notice that its interpretation of this query is actually changing. I think we've got some other examples. I can say, whatever, barbecue near Charlottesville. Can't spell. There, Charlotte gets an ad. Charlottesville. And I've got some other examples here I'm not going to go into for the sake of time, but the interesting thing you can do with this, based upon the way it's structured, because it's explicitly parsing out each part of the query, and then it enables things like action or commands to be able to operate on different tokens in the query. As you're typing and as more information comes in, the interpretation of the query can change in a very nuanced way. For example, if I type, if I just type Haystack, it understands Haystack as a location. That is the Haystack conference. And searches for the name Haystack Conference as the title. But if I then type Charlottesville, Haystack Charlottesville, oh, that's interesting. Why didn't it? Hold on. Oh, yeah, that's why. That was my point. Haystack Charlottes. Notice it's not doing a lat long search. Why is that? Because my logic here is if I say in, then it does a radius search. If I just search for the keyword, then I'm actually just doing a text match. You might want to change the way that behavior is interpreted, but you have this very powerful nuance here to be able to handle things. Similarly, I didn't get this one quite implemented before the talk, but if I said, top barbecue, this isn't going to work, I don't think. Probably going to error out. Top barbecue near Haystack. Yeah, it fails down here. I didn't get this one implemented, but basically it says, I'm looking for something called this popular, and that should modify the thing that comes after, which would be barbecue. And then it would do the near Haystack stuff as well. So I could, instead of just searching for barbecue by relevance near Haystack, I could search for, what is the most popular place, if there's a popularity field in my index, et cetera. So this is just, some examples of sort of how this stuff can all be applied to take the user's query and inspect the knowledge graph that you have in your inverted index and automatically learn relationships and apply them. Eric Hatcher mentioned yesterday, very beautifully talking about Ted Sullivan, how he was sort of ahead of his time. He was always talking about leveraging facets and leveraging these unique insights in the inverted index to be able to learn the semantic meaning that we could use to enhance queries. I'd like to kind of think of this as an extension of what he worked on for many years. But there's lots of really interesting things that you can do here. And to wrap us up, there's a lot of work going on in question answering these days, and there's different approaches. One of those approaches is building a giant knowledge graph and trying to traverse. Another approach is trying to build deep learning models that can parse and understand text. And one of the popular ones is Dr. QA. I've played with it. It's actually really good at answering factual questions that are simple, like, who is the president of the United States? But when you ask it, or even who is the brother of George W. Bush, or who is the brother of the president, maybe even in a certain date. But once you get more than like 1 or 2 levels of relationship deep, they just break, they fall apart because they've got sort of a surface understanding of the text and the models and the way they're working. So having a knowledge graph that you can actually explicitly traverse for some of these things is really useful. And in my examples, again, I didn't get the popular one implemented, but barbecue near haystack, fine, that's awesome, cool parlor trick. But popular barbecue near haystack, movie theaters near haystack, hotels near popular barbecue in Charlottesville, barbecue near airports near haystack, hotels near movie theaters in Charlottesville. These are all kinds of questions that you can answer by basically just having these semantics that more or less map to how our brains interpret queries, but being able to do it very fast and flexibly using terms and tags and what have you is kind of what I was trying to show today. And sort of the power of the text tagger, the knowledge graph capabilities in Solr, and both the ability to learn the strength of relationships between things semantically, and also to be able to explicitly traverse from a known entity to another known entity across documents and fields. That's just the beginning, but unfortunately it's also the end of our time today. So hopefully that was useful, gave you some things to think about and a sort of different way to approach search and how not just building a knowledge graph, but how you can actually use the search engine as a knowledge graph and have the knowledge integrated in the search engine and use it to power real semantic understanding and interpretation of users' queries. So again, I work for Lucidworks. A lot of these techniques we have built into our Fusion product. If you're interested, I'd be happy to talk to you about that. But otherwise, hopefully, there's some good takeaways you guys can leverage. Happy to take questions after if anybody wants to come up. And yeah, thank you.
Thank you, Trey. Thank you, Trey. Huh?
Oh, I just want to say there's snacks in the 3 o'clock.
Yeah, there's snacks. I think we have. We don't have a whole lot of time for questions, but we can. So, raise your hand if you have a question.
Thank you. Hi, Trey. This is a great talk. I know we're all into semantic search, and this is a new dimension, the knowledge graphs. So I'm sure we are all going to try this. So my question is, do you see any application or domain where knowledge graphs are really not applicable so that I will not waste my time?
Can you list all the domains you're in?
Document search, we are all into document search, finding people, relations, entities. Find things, basically, not strings.
Sure. So the semantic knowledge graph specifically is a general tool. I think of like a data scientist toolkit. So you can use it to, I showed a few, I have like 10 more examples I didn't put in this talk, but were in my talk from last year if you want to check it out. But you can use them for, you can use it for everything from, removing noise in data sets to discovering anomalies to, I showed the content-based recommender example where I can take content and match so I don't have the cold start problem. I showed concept expansion, the classification. I basically showed with that restaurant example, filtering down to restaurant. There's a lot of things you can do with it, just like you could with an explicitly built knowledge graph that you maybe built in Neo4j or something like that and spent lots of time building and pruning and what have you. Yeah, sure, there's plenty of use cases where it doesn't apply. For the semantic knowledge graph specifically, and just to back up a little bit, I talked about 2 things, the semantic knowledge graph and just graph traversal in general. So that example where I was going from haystack to the violet crown, that wasn't using the semantic knowledge graph. That was just using a regular graph traversal between 2 documents that represented entities. So you can use that wherever, but the semantic knowledge graph specifically is really built on this notion that similar words appear in similar contexts. So the one case where you're not going to have any success with the semantic knowledge graph is where I've got documents that are completely partitioned, completely disjoint. So for example, Wikipedia, while data scientists use it for, it's like their starting data set for almost everything, the semantic knowledge graph does a really bad job on Wikipedia. Why? Because every Wikipedia article is about one thing, typically. And there's some overlap for very popular terms or people or what have you, but generally the documents are fairly disjoint. And so you don't find a lot of overlapping terms and phrases used across them, so it's not going to work well there. Something like Stack Exchange, Stack Overflow, a job search website, a news website, anywhere where you've got a bunch of documents where there's similar things being talked about and similar terminology being used in different places, it's going to do really, really well there. Yep.
Thank you, Trey. I think we want to go have some snacks and walk around. Can I have another round of applause for Trey?
Thanks, guys.